So the speakers, as you can tell, have put a lot of work into these presentations, and I've had the good fortune of attending some of the rehearsals. And a couple weeks ago, I learned a new word, and I came home, and my daughter's 8 years old. Her name's MJ, and she said, "How did work go today?" And I said, I learned a new word today. It was called biomimicry. Do you know what that is? And she said, "Oh yeah, that's a new approach to innovation by learning from nature's time-tested patterns." What they teach these kids these days. So biomimicry is really, really cool. Let's kick it off. Please welcome to the stage Bob Treiber from Boston Engineering. Let's see their video.
But Boston Engineering, we want the hard crossword puzzle, right? Nobody wants to work on an easy crossword puzzle. You want to work on a tough problem.
At Boston Engineering, we believe we innovate the future. We're solving problems that seem to be unsolvable. There's nothing like it in the world.
So Boston Engineering got started as the core, the inside of the products. Over the years now, we've evolved and we've matured and we've expanded into not only doing just the inside of products, but also the external part of the products now. I'm talking about industrial design. I'm talking about usability. I'm talking about human factors.
Customers come to us because they want to go to one place where the resources are all in-house, that can be applied to the development of a system-level solution that meets market demand.
In our team, we have folks with many different backgrounds coming from many different industries, and so we're able to draw on the variety of talents that they have to put together teams that are appropriate for each customer's project.
We built a company that allows us to tap into the entrepreneurial energy that our people have. These people work tirelessly to solve some of the toughest challenges in the world. It's not about a 9-to-5 job for them.
We've been doing this a long time, and I've never heard an engineer say it can't be done. So you're trying to push the edge of physics or find out where you can be, and those are the kind of folks here that are motivated to be here and do the great work that we do.
Boston Engineering. Imagine the impact.
Please welcome to the stage Bob Treiber.
My name is Bob Treiber. I'd like to speak to you this morning about a new direction in innovation, reverse engineering, 20 million years of evolution, or what I like to call how biomimicry can help you with your next new product development challenge. Before I get started, though, I'd like to thank you all for being here, and I'd like to thank PTC for inviting us all down here. This is by far the single coolest place to go to a trade show. So biomimicry, you heard a little bit about it just before then. What is it? It's pretty much what it sounds like. You mimic biology, copy biology, or you learn from biology what nature has evolved to master or perfect over millions of years of evolution and trial and error. Probably the best known applications of biomimicry are found in flight. The owl, commonly called the silent killer, has evolved serrated feathers to make it more quiet in flight. The seagull has evolved movable, retractable wings to help it adjust to gusts of wind. The eagle has developed at the end of its wings that help it give it lift as well as maneuverability. Engineers have studied these features of these birds to help them design better airplane wings, better wind turbines, and even quieter fans on our computers. Closer to home, you're probably all familiar with the smell of natural gas. Natural gas in its natural form is odorless. It has no smell. We humans add an odorant to it so that we can detect it in the event of a gas leak before we strike a match or do something else that could be catastrophic. Well, that chemical that we add is called mercaptan, and chemists and scientists and engineers studied our friend the skunk to develop that. So what was our challenge? what you see behind me is the state-of-the-art in underwater ROVs, remotely operated vehicles. They've gotten a lot of attention recently, unfortunately, in the search for the missing Malaysia flight number 17. These ROVs are designed to go deep, and they're designed to explore. They are very, very good at moving in straight lines and following a methodical search pattern, kind of like going forward and coming back like you would when you cut your lawn. They are not very good at maneuverability. The Navy, however, challenged us at Boston Engineering with quite a different mission. They asked us to develop an autonomous vehicle, underwater vehicle, that was highly maneuverable and one that could work in the shallowest of waters. Think about our shores and our rivers. So, what did we do? Quite naturally, we thought about a fish. Now, as it turns out, there are more than 29,000 species of fish in the ocean. So the first question was, what do we do? Study a fish. The second question was, which one? Well, we chose the tuna. As it turns out, while we all think of tuna tasting very good, it is that, but it is also one of the fastest fish in the ocean. It can reach speeds of over 60 miles an hour. It is also extremely maneuverable. It's able to turn 180 degrees in its own body length. Most importantly, it is the most efficient swimmer in the sea. That is, if you measure its caloric intake by what the fish eats, and then you measure its energy output by how fast, how far, how forceful the fish moves through the water, and you measure the difference between input energy and output energy, you're not going to find a more efficient fish. Obviously, why is efficiency important? For all of you with cell phones and laptops, how long and how far can you go before a charge? But even more importantly, when we're talking about underwater operations, it's how long and how far can you go before resurfacing. So, the fish has had 20 million years to evolve to be this voracious, perfect swimming machine. We don't have 20 million years. We've been at it for about 7 years. So why don't I show you how far we've gotten in those 7 years? Can we bring out the BioSwimmer, please? Thanks, guys. So this is our BioSwimmer. The Navy likes to call it Silent Nemo. We actually have two versions of the fish. A lot of times we just call it the fish. We have two versions. What you see here is the BioSwimmer, which has the natural fish tail. We have another version called the BioSwimmer. I'll show you a video of that in a second. That has an additional propulsor on the back that gives it a little extra energy. It still has the natural swimming motion of a fish, but it has the added benefit of the propulsor in the back. So we picked the tuna. Okay, that's a good first step. So what did we do from there? Well, the first thing we did was we measured everything we could about the fish. We went up to Gloucester, fishing town up in Massachusetts, met the fishing boats as they came in, and we bought ourselves a couple of tuna right off the boat. Didn't clean them. Took them right to a friendly machine shop that we work with who had a coordinate measurement machine, CMM. For those of you who don't know what a CMM is, it's a machine that allows you to reverse engineer a solid object. So it has a probe, and you can pick points on the object and allow you to make a point cloud of that object. We took that point cloud and we imported it into Creo. And then from there, our mechanical engineers were able to replicate exactly this fish. And this is the exact replica of that fish that we put into that machine that day. It was exactly this big, this wide, same dimensions, exactly. So we figured out how to do the mechanical part of the fish, the physical fish. the next part was we had to figure out how it works inside. So we worked with biologists to study the skeletal structure of the fish. We studied with the biologists about how the muscles work. And we watched a lot of video about how a fish swims through the water. It turns out the tuna only moves its rear third. It's only the tail that actually moves when a fish is going through the water. The front 2/3 of the fish remain focused on the target as it swims through the water. Quite naturally, we did the same thing. Only the rear third of our fish moves as it goes through the water. The front third of our fish is where we store control and navigational electronics, as well as forward-looking sensors. And then the middle third is the payload area of our fish, where we can store the client's sensors or other things that the Navy may want us to carry. So that's all real cool, and that's the physical part. You've heard a lot about PTC's concept of the digital twin. We did something fairly similar. As you might imagine, the motion of the tail is at its core a spline motion. However, how to fire each segment of the tail, when and at what angle, that's pretty tough to figure out. We did the best we could in reverse engineering it, but then we developed in software what we call a genetic algorithm. So we broke down each piece of that swimming motion into small parts. And then through a series of design of experiments-like activities and statistical analysis and the computing power of the DSPs on board, we're able to actually mutate those parameters as the fish swims. So if you go back to this digital twin idea, we're able to instrument the fish and measure how well it's going through the water. We can measure the speed and the force with which it's going through the water. At the same time, we can mutate the swim profile as it goes through. Those mutations that add force or make it swim better, we keep. Those mutations that don't make it better, we toss away. So we can literally evolve the fish. We can take 20 million years of evolution and recreate it here with the power of the DSP. This next video shows the early prototype of the first time we actually got the fish swimming. This is the BioSwimmer, as I mentioned. It's got the propulsor in the back, and you can see, in this case, it actually swimming backwards. You can see the pectoral fins controlling the depth. This was the first time we were successful. The guys got it on video, which was fantastic. I'm pretty sure it stopped working as soon as we turned off the video camera. And it was a deliverable for the Department of Homeland Security, so even better, we actually got paid. So, all very good, very cool. These guys were all jacked up when we finally got this thing going. As soon as we got it swimming, you can imagine we wanted to go deeper and faster, and as soon as we did, we ran into new challenges. We learned a lot more about the compressibility of the materials we used and how that affects the buoyancy of the fish. So, quite naturally, we went back to biomimicry and we studied the fish, the tuna, and how it deals with buoyancy. It turns out the fish has a series of swim bladders that help it maintain buoyancy. So we learned a lot from that, instituted some of those properties, and eventually overcame those challenges to the point where we got to real field trials with the United States Navy. This is a picture of our fish out at Fall River, Massachusetts, at a place called Battleship Cove. I usually get two questions when I show this picture. The first is, what's the green hose? And the second is, why orange? Well, it's not a green hose. It's a green communication cable. The fish is autonomous. I mentioned that earlier. So while we can control it remotely, for these field trials, it operates on its own. That is, we program it on land, and then we launch it. It executes its mission. If all goes well, it comes back to us. The green communication cable is connected to a towed array, a communication buoy, if you will, which streams back all the data, everything that the fish is sensing, everything that the fish sees, all the forces that we can measure, and of course, all the angles of the tail as it swims. We take all that data back, and just like the digital twin, we feed that back into our design to improve both the software algorithms and the physical design of the fish. Now, in the event that all does not go well, we put an orange shroud around it so that we can hopefully find her. This next video is from a successful field trial down in the Gulf of Mexico. The guys had some fun and took some video of the fish after it had completed its mission. So they were doing a little celebration. Now, keep in mind, the fish is designed to swim underwater. It's not as elegant when it's above the water, but nevertheless, you can see the fish and its maneuverability here on the surface. That's the USS Houston in the background, and you can get an idea for the maneuverability of the fish. So by now, you have an idea. That fish is probably 6 inches longer than this one. But for the most part, you get an idea for the scale of the fish. It's pretty cool. Does all those things, swims like a fish. But what I didn't have an appreciation for until we actually simulated some of these missions is the scale of our underwater assets. And what I'm going to show you here is a mission simulation we did of our fish, the BioSwimmer, inspecting an oil rig. And you'll get an idea for the enormity of what we're talking about underwater. And of course, if you watch the fish go through its two things that impressed me: size, number one, and number two, all the hiding places in there that bad guys could hide contraband that may be harmful to us. And so if you ever wanted to inspect something like an oil rig, you'd have to have something like a fish to get in there. So it's pretty simple, right? You copy a fish. Well, it is that simple. And that's, by the way, how things should start. Everything should start simply, right? But I'm sure you folks know in what you guys do every day that nothing gets done without a bright, motivated team of professionals focused on achieving a goal or a mission. We're blessed at Boston Engineering to be loaded with those kind of folks, and I'm lucky enough to work with them every day. Second thing that we're blessed with is, as a small business, we've been fortunate enough to win grants called Small Business Innovative Research from the United States government, specifically our U.S. Navy and our Department of Homeland Security. Without those two things, great people and the funding of our United States government, what was thought to be impossible would not have come to the reality that it is today. So where do we go from here? It's pretty apparent that underwater robotics is following the path of both ground robotics and aerial robotics today. It's not hard to imagine swarms. You've probably heard of swarm technology. It's not hard to imagine swarms of aerial robots in the sky controlling a mission, working together. Similarly, it's not hard to therefore imagine schools of underwater robots, coordinated, connected, networked, and working together. And then if you go a little further, it's not hard to imagine swarms in the sky, assets on the surface, schools underwater, all connected and all working together to patrol our shores, protect our borders, and protect our American warfighters. Pretty powerful that what our armed warfighters can do with these kind of tools. So, all very cool. It's great to work at Boston Engineering, to work on this cool stuff. We're very proud to be protecting and saving lives, especially of our American warfighters. But I want to leave you with this final thought. It all started with the idea to copy a fish. So maybe the next time you guys are up against a tough product development challenge, maybe biomimicry can help you. Thank you for listening. Enjoy the show.